So we're going to focus on the solar heating mechanism of lift. There are other ways to get lift. For instance, frontal activity could initiate lift. Mountain waves could do it. But most of the time when we're soaring, we're going to be taking advantage of solar heating. So let's make this, we'll draw a nice picture here. Let's make this a nice sunny day. And the sun will be heating the ground. Let's make this semi-realistic for Shirley, New York. We'll have a nice thick foresty area here. Kind of fail at drawing trees, but whatever. We have a river. This is a cross-section in case you couldn't tell. You know, maybe another field. Couple hills. Then we have some shopping centers. Black asphalt parking lots. And we got some farms too. Now, different surfaces are going to absorb heat at different rates, right? And if you're not convinced of this, you know, just walk outside on any hot, sunny day in bare feet, step on your driveway, and then step on the grass, and, you know, see if you feel any relief stepping on the grass. And so obviously the surfaces heat at different rates when you have sunshine, and the surrounding air, like the air immediately above it, does too. So all of this air on the surface will have slightly different temperatures, and you could probably guess the parking lots and the farms are going to have the warmer temperatures. So you'll get some nice air, a nice chunk of air sitting over, let's say, the parking lot that is warmer than the surrounding air, right? This is all the surrounding air, and you have the parcel of air sitting over the parking lot that is warmer. And because it is a little warmer than the surrounding air, it is less dense, so it will go up. And by the way, you can see right away on like a windy day, you're not going to get solar heating type of lift because the air mixes better, and you're not going to get warm chunks of air just sitting over the hot surfaces like that. But anyway, that's how you'll get a solar heating trigger of lift. So on this day, if we want to sketch the parcel temperature profile on this sounding, let's say this was the sounding at the time. Our surrounding air, all this orange we drew here, that would have the temperature of whatever the ground temperature is that's indicated on the sounding. That's like, what, 13-ish degrees or something like that. And the bubble will be a little bit warmer, hopefully, anyway. So that will be, let's say, a couple degrees warmer. I need to make it a little more than that. Yeah, a few degrees Celsius warmer. So as this rises, as this parcel rises, it will follow the dry adiabatic lapse rate. Now, as you can see, very quickly it intersects with the environmental temperature. Here's a key fact. In order for a parcel to continue to rise, it has to be less dense than the environmental temperature, or than the environmental air. So therefore, the temperature of the parcel has to be warmer than the temperature profile in order for the parcel to continue to rise. So in this case, you'll see it's not going to go very far. It'll get to the environmental temperature, and it's not going to create a very high thermal at all. Now in this case, the bubble was barely heated, just enough to start to go up. But let's say you had a little better heating than that. Let's say this was significantly greater. The temperature of the parcel was significantly greater than the surrounding air. Let's say it was where this black dot is, right there. If it heated that much, what'll happen is it'll have a dew point there, right? Just because it heats up doesn't mean its water content is going to change. So it'll follow the dry adiabat like that. Dew point will follow the constant mixing ratio until they condense at its lifting condensation level. Then it'll follow the moist adiabat, and it'll keep going up until basically it intersects with the temperature profile. It won't just stop there, it has to decelerate. But you can count on it going up until it intersects the temperature profile. So what'll happen is you'll get a cumulus base here, and you'll get a nice cumulus cloud until it stops rising. So actually, even though you'll get lift within the cloud itself, you'll be in IFR, but you can count on soaring all the way up to this base here that you found. Now, to be honest, this is a stretch, having the parcel heat up that much. However, it does look like this was a morning sounding, probably taken from a morning weather balloon launch. What sometimes happens in the afternoon is you'll get an inversion to break. So actually, this is a pretty strong inversion there. I would bet this is a morning sounding. And in the afternoon, the sounding probably looked something like that. A dry adiabat all the way to the surface. So now let's say that was the case. Then all you would need is just the bare minimum amount of solar heating. You know, if in that case this parcel here was heated up just a little bit more than its surrounding air right there, then it would be able to lift itself, let's see, all the way up to there, and then form a cumulus base, and then go up a little bit more. So notice this is really good because we've seen that the temperature profile, the actual environmental temperature measured by the weather balloon, is just as steep as the dry adiabatic lapse rate, so it can support solar heating. Now let's say you get a little bit more heating. Let's say a parcel is heated to maybe here. Alright, so what'll happen now? Well, the dew point will be the same. It'll follow the constant mixing ratio. Let's see. So it'll go up to about there. And look what happens now. This is where the cumulus cloud base is. It's going to keep going up. But there's nothing to stop it. It's continuously warmer. If we follow this moist adiabat, it's still warmer than the temperature profile, almost to the top of the tropopause. What's that up there? Like 30,100. I'm imagining that's feet. I can't imagine that would be meters. But still, that is basically the top of the tropopause. So what's going to happen? Any guesses? There's your cumulus base. Look how tall this is. You're going to get thunderstorms. Boom! This sounding is actually really favorable for thunderstorms, it looks like. One last concept I want to discuss is it has to do with buoyancy. Basically, the bigger difference you have between the parcel temperature and the environment, the stronger your lift is going to be. So if you just had the bare minimum solar heating like that, assuming this temperature profile drops adiabatically in the afternoon, there will be a push upwards with this parcel of air, but it might not be strong enough to counteract your glider's sinking rate. Whereas if you had a little bit more heating, then the temperature difference is more. Therefore, the parcel will have more energy to lift. There's actually something called the thermal index that takes the temperature of a parcel lifted from the surface and subtracts. Actually, it's the other way around. It's the environmental temperature minus the temperature of a parcel lifted from the surface. That's your thermal index, and they say basically -2 or lower is good for lift. I personally recommend just getting used to looking at soundings to predict lift if you're a glider pilot. I don't think any indices or numbers can replace the actual understanding of how this works, but that's just my opinion.